a rectangular matrix with R rows by C columns that has a full column rank, meaning it has linearly independent column vectors, can be factored as a product of two matrices Q and R. And this is the QR decomposition of A. Now if we suppose the matrix A is made up of the column vectors A1, A2, up to AC, and similarly the matrix Q is made up of the vectors Q1 to QC, and Q has orthonormal column vectors. So A1 can be written as the inner product between A1 and Q1 and in the direction of Q1 plus the inner product between A1, Q2 in the direction of Q2 and so on up to the inner product between A1 and QC in the direction of QC. So if you repeated this process for each vector A in matrix A, you'd be summing up the projections of A2 onto the orthonormal column vectors of Q. So you just replace A1 with A2, and continuing this process up to AC, we have the following expression. So we can write this in matrix form by putting A on the left hand side. So we have the matrix of the column vectors A1, A2 up to AC, and that's equal to Q, which has the orthonormal column vectors Q1 to QC, and that's multiplied by the R matrix. So A1 is equal to Q1 by the inner product between A1 and Q1 plus Q2 by the inner product between A1 and Q2 and so on up to QC by the inner product between A1 and QC. And similarly, we have Q1 by the inner product between A2 and Q1 plus Q2 by the inner product between A2 and Q2 and so on up to the inner product between A2 and QC, and that's multiplied by QC. And let's make a bit more space. So if you continue this, you'd have the inner product between AC and Q1 and the inner product between AC and Q2 and the inner product between AC and QC. So now let's remove this and look at our matrix form. So I'll just put that up here. And remember the Gram-Schmidt algorithm, which converts a basis into an orthonormal basis. So we'd start with A1 and set Q1 to be equal to A1. So therefore A1 is not orthogonal to Q1, so this entry is non-zero. And if you continue the Gram-Schmidt process, you can see that A1 is orthogonal to Q2 and Q3. And if you had more basis vectors, this will continue up to QC. So therefore the inner product between A1 and Q2, A1 and Q3, and A1 and QC is 0. So these entries are all 0, and we don't need to compute them. And similarly, if we look at the basis vector A2, we can see that it's orthogonal to Q3. But it's not orthogonal to Q1 and Q2, as we can see. And if you continue this, it'll be orthogonal to Q4 and up to QC. So therefore, the entries below the diagonal are all 0. So therefore our matrix R is an upper triangular matrix. So we have our matrix A is equal to Q by R. And now we'll follow this with an example. Let's decompose the matrix A with linearly independent column vectors, being A1 with components 1, 0, 1, A2 with components 1, 1, 1, and A3 with components 1, 1, 0, into a product of Q and R matrices. Now Q is a matrix of orthogonal column vectors, which we obtain from the following column vectors using the Gram-Schmidt process. So we have Q1 being set to A1, and Q2 is obtained by subtracting the projection of A2 onto Q1 from A2. So the inner product between A2 and Q1 is 2 over the squared norm of Q1, which is root 2 squared, and in the direction of Q1. So that's the projected vector A2 onto Q1, and then we subtract this from A2 to get the orthogonal vector to Q1. So 1 minus 1 is 0, 1 minus 0 is 1, and 1 minus 1 is 0. So our vector Q2 is 0, 1, 0. And to obtain Q3, we subtract the projections of A3 onto Q2 and Q1 from A3. So we have A3 minus the inner product between A3 and Q1, which is 1, over the squared norm of Q1, which is root 2 squared, in the direction of Q1, and minus the inner product between A3 and Q2, which is 1, over the squared norm of Q2 in the direction of Q2. So therefore, the first component of Q3 is 1 minus a half minus 0, which is a half, And the second component is 1 minus 0 minus 1. And the third component is 0 minus a half minus 0. So you can verify that all these vectors are orthogonal to each other by taking the inner product between them. And our matrix Q consists of the normalized vectors Q1 to Q3 in each column of the matrix. So normalizing Q1 gives 1 on root 2, 0, and 1 on root 2. And normalizing Q2 gives 0, 1, 0. And if you take the norm of Q3, you'd get the square root of 1/2 squared plus 1/2 squared, which is a square root of 2/4 or 1/2. So that gives a norm of 1 on root 2. And dividing a half by 1 on root 2 gives root 2 on 2, which is the same as 1 on root 2. And then we have 0, and minus a half on 1 on root 2 is minus root 2 on 2, or minus 1 on root 2. So that's our Q matrix of orthonormal vectors. And now we can obtain our R matrix. So the first entry is the inner product between A1 and Q1. So that gives 1 on root 2 plus 1 on root 2, or 2 on root 2. And the entries below the diagonal are 0. And then in the next column, we have the inner product between A2 and Q1, and A2 with Q2. So the inner product between A2 and Q1 is 1 on root 2 plus 0 plus 1 on root 2, which is also 2 on root 2. And between A2 and Q2, we have 0 plus 1 plus 0, which is 1. And below the diagonal, we have 0. And now we take the inner product between A3 and Q1. So that gives 1 on root 2. And A3 and Q2 gives 1. And A3 and Q3 gives 1 on root 2. So that's our R matrix. And this is our QR decomposition of the matrix A. And I encourage you to evaluate this product and verify that it gives you back the matrix A.